to everybody. Welcome back. It is my great pleasure to introduce Professor Ioannis Athanasopoulos from University of Crete in Greece. Ioannis is actually my eldest academic brother. He was technically the first student of Luis. So throughout the years, he has done many significant and very important contributions to many fields in analysis. I would emphasize free boundary problems, where he has many deep works in the Signorini problem, lower obstacle problem, caloric functions in Lipschitz domains, free boundary regularity in parabolic phase transitions, and so on. He is always a very funny person. If you know him, is a very funny person to be with. And then I was the other day chatting with him on the hall and said, "Have you ever been in Brazil?" And he looked at me and said, "Well, I was in Brazil in the viscosity sense." I said, "So what do you mean?" And then he said, "Look, many years ago I came to visit Argentina. The Iguazu Falls, the waterfalls here, and there is the Iguazu Falls is on the border of Brazil and Argentina." And he said, "Oh, I was in the Argentinian side, but I came across a little bit to the Brazilian side." So now that you are visiting Brazil in the classical sense, I really hope this is the first visit of many that you do in the future. Thank you very much.
Well, I would like to thank very much the organizers that gave me this opportunity to visit Rio and to give a talk. I have to apologize. I put IPMA, it's IMPA, okay? And I have to say something about, after this traumatic experience that Luis had with me, it took him 10 years to recover, so he can get a new student. Well, anyway, it was the same time. It was the same time. Yeah. Okay, so this is a joint work with Luis and Milakis, a former student of mine. And okay, parabolic obstacle problems. Which parabolic obstacle problems? The first one, oh, the other way around. We all know the thick obstacle. You have a nice poster, right? And you have the pau de açúcar, and you have a sheet on top, right? So imagine this pau de açúcar moves up and down or change a little bit shape. So this is the parabolic obstacle problem, right? And the other parabolic problem I like to consider is the thin obstacle problem, or time-dependent Signorini problem, or boundary obstacle problem, right? Which is almost the same as the thick obstacle, but everything takes place on the boundary. Let's take the flat boundary R, and the gamma is a part of the boundary. So the inequalities there is the normal derivative and the function, right? That the function has to stay above the obstacle, right? And together they have to be 0. And outside, you have a parabolic equation, okay? Now, a slight variation of this is the dynamic thin obstacle, we call it, which you add the ut and the Rn minus 1, right? And of course, you have the same thing that it's parabolically inside. This is related to the normal derivative. Actually, it's like they have Laplacian. So if you want to restrict yourself on the hyperplane and look all of it, then you have the fractional parabolic, the fractional obstacle problem, Okay, we have these assumptions and P and the obstacle, and then here is the problem, right? When s equal 1/2, I said, is exactly there's a relationship with the previous one, extended with the Neumann-Dirichlet map. And of course, you can do the same thing even for any s, right? As Luis and L squared, they say Luis and Luis Sylvester, they show that you can extend the solution inside parabolically. Well, they've done it elliptically, but it's trivial to consider it parabolically too. Okay. And then there is the fifth problem, which is the nonlinear integral operators. So you cannot extend inside. So you restrict it only on the boundary if we go to the first case. But here we consider in all Rn, and we consider the nonlinear integral operator, and the same, more or less, the same inequalities hold. Now, all these five prototypes, let's say, of obstacle problems, they share a common property. We call it quasi-convexity. You see, each one of them can be written as the minimum of two linear monotone operators. For example, for the thick obstacle is the heat equation, one monotone operator, and the other is the u minus psi. Right? So all of them can be written like that. So the second order incremental equations, right, they are super solutions. Right? And they satisfy a minimum principle. So, and this is true even if you take it to the limit. So the second derivative, not only the space, we only have used the space, here the time too, right? This is bounded below because from the data. It's easy to see when the obstacle does not touch the data, it's above. Therefore, there you have a classical parabolic problem, right? So you solve it, you go a little bit inside, very smooth. So there, where you do the second derivatives can experience the minimum, right? Now, okay, the issue here is not to find the most general boundary data to see where this quasi-convexity holds, but we believe a barrier argument we should do, so we can have it in much weaker data. Okay? Now, okay, so we have this quasi-convexity. So what? Right? Well, this is an improvement of the optimality of the UT. In most problems, the UT was just bounded. Right? In order to have some improvement in that, you need some information about your free boundary or some other given property. Okay, so in the literature, there are only 3 places where the UT was continuous. And there, you assume that UT was already, or was constructed in the problem. The first one is the one-phase Stefan problem, which you already have integrated the original Stefan problem, because you have some monotonicity of the free boundary moving in one direction. So UT was always positive, right? The same thing, this is a thin version, the one I was trying to generalize when Luis done with Friedman, right? And the third one, just recently, right, when they took this parabolic obstacle problem, right, and they took the obstacle does not depend on t, therefore, from there you can infer that the ut is positive. Okay, now let me show you how you really can get this continuity of the positive derivative. This is, in some sense, a little bit, you can understand that when you're peeling up something or you're lifting the obstacle, you expect that to be continuous. But when you try to cover the obstacle, most of the time you cannot do it very smoothly. So the negative part cannot be continuous, as many counterexams show in the thick obstacle case too. Okay? So this is the best in some sense. Okay, let's see how you really do the proof of such thing. And goes for all of them the same methodology. Penalize the problem, subtract the obstacle. It's better to work with a zero obstacle. So subtracting the obstacle, you throw it on the right-hand side of your equation. Right? Differentiate with respect to time, and you work with a derived equation. So let's see what happens with a thick obstacle. Okay. So we take the penalization, which is a standard penalization used in the book of Devaux and Lyons, which is in French is inéquation, or in English is inequalities of mechanics and physics. They have all the problems, they do that with this penalization, they do it, right? So you penalize, you take the derivative, you subtract, you take the derivative, and you look at the equation. So this is the equation. So what do you do that now? So the basic lemma is this. We normalize it, so okay, to look better. So it's between 0 and 1 in a cylinder in the past, right? And the lemma says, if the average, okay, I don't have the average because 1, I put it like 1, so it's the average. If the average is close to its maximum, that's what it says, 1 is the maximum, sigma is small, then the u epsilon has to be bigger than a half in a smaller cylinder. If not, then u epsilon is smaller. So in a sense, we have increase in the oscillation, right, has diminished, right? Okay, now, let's see how you prove the first one. I forgot. So you write it as 1 minus u, v, and you get this equation, right? And you multiply, right, with this cutoff function, and w minus k is some positive number, and you integrate by parts, right? So you have a term on the right with a t derivative of the penalized function. That's a dangerous term. So you want to get rid of that. So you integrate by parts in t, right? So you throw the derivative here, but we have boundary terms. The bottom is 0, but the top is this. This is on top. The 0 is on top. But this is no problem, because beta is negative. The other is positive, so it goes away. Here is where the quasi-convexity enters. When you take the derivative here okay, you have a product, so when you take the derivative of this, there's no problem. The problem is when you take the derivative of this. W, if you remember, was 1 minus v, right? Taking the derivative, it's like the second derivative in t. But the second derivatives are bound below, right? And the minus with the negative thing gives you positive, and this is, you have a bound on top, right? But you see that this works for the positive thing, but not for the negative, right? So you get the energy inequality. So this is the energy inequality, and here is the C. The constant depends on this and this. Okay? Now, once we're here, we have the De Giorgi approach now, right? You have the energy, and you make this standard thing introduced by De Giorgi, right? And you get an iteration of this integral. And the iteration is this, right? This comes out even in the one that De Giorgi did, right? The exponent and things like that. And that will give you this exponent, 1 plus something, right? Will give you that this integral will go to 0 if this is smaller than this number, which we call it sigma, right? So, now what happens with the other one? The other one, okay, it's more, so if this is not true, I mean, if this is bigger than sigma, then you have this. Then this already here makes it a subsolution. So when you go back to the equation, the term, the dangerous term, which is the beta, the penalization, goes away. Because the derivative is positive, and you multiply it with a positive thing, right? And the derivative is positive. Yeah, I don't have that, but it comes out to be negative, or in the equation is positive, so you have bigger or equal to 0. So when you integrate by parts, it becomes less or equal. So no terms, no dangerous term of the beta term. Therefore, the De Giorgi dyadic sequence of normalized truncation and all these, right, will go through. You need the isoperimetric lemma of De Giorgi, right? And as I know, first time it was written, it was in this paper with Ruiz and Vasseur, and which takes this form. So the lemma says, okay, what it's supposed to say, right? That this small enough, this integral, and that will give you the proof for step 2. So you take step 1, step 2, right? Put them together, you iterate n times, and you get the C alpha. No, not C alpha, sorry. You get just continuity, some modulus of continuity, okay, independent of epsilon. And then from the penalization techniques, we know we can go to the solution. So we have the continuity of the positive time derivative. Now, what happens with a thin obstacle? The same thing. You have to change a little bit the lemma. The lemma takes this form, right? You have this term, and you have this term. This cylinder, right, is center at the free boundary point, which is on the hyperplane. So you consider it in the xn, the positive xn so it's a square cylinder, right? And so the basic lemma takes this form. There exists a sigma such that if this is less than sigma, then you have that, and the second is this. Now, when you try to work with that, right, the iteration scheme, you don't get as nice as in the previous one, right? You have it, you have this, you jump from m to m minus, or from m minus 2 to m. So you skip a step in your iteration, right? But yet, this will be enough to tell you that this will go to 0. So again, you get the modulus of continuity, and if you are very careful, with a scaling, you get exactly C alpha. Although in the previous one, it's not nice. Here, you get the C alpha, for some alpha. Okay. Now, for problem 3 and 4, if you refine more the Georgi approach, right, as it was done first with Luis and Vasser in the quasi-strophic, right? The drift diffusion equation with fractional diffusion, quasi-strophic. And then for a general fractional derivative, later we did with Luis with the temperature, which is actually, this is more or less like the thin Stefan problem, if you're going to call it. I mean, Stefan conditions and the boundary in some sense. Okay. Now for the nonlinear integral operators, which you cannot extend inside, right? Again, you can refine even more the Georgi technique, right? They use it here, right? So readjusting for our problem, it goes through. The same idea, same lemma. Okay. Now, from now on, I will concentrate only on the thin obstacle to see further implications of the quasi-convexity. Okay, because we have a clear picture of what goes going on. I mean, we have finished it, but the others we still have incomplete. They're still incomplete. So, okay. So the first thing you can get here is, again, as I said, it's easier to work with a zero obstacle. So you subtract it, right? You don't put just equal to 0. You want the obstacle inside because the obstacle has to depend on time, and if you put it just 0, then the time disappears in some sense. Therefore, you have to subtract it nicely, right? And throw, right? And you throw it here, which is this. So the obstacle, you can extend the obstacle inside. Here you can be a little bit crude. You don't care because U is not, you don't have a condition that U has to be above C inside, so you don't care how you do it. But anyway, okay, so you can make it so it can be independent of Xn. Okay? Now, once we have this quasi-convexity, we can prove that the gradient, the space gradient, is C1/2. Not just C alpha, C1/2 1/4 if you consider a parabolic scaling, okay? The time. Now, actually, partially, this problem is, it is in the appendix of the work we have done with Luis some time ago for the elliptic. We had a monotonicity formula, right? And from there we could do the 1/2, exactly the 1/2 regularity of the gradient. And the appendix, right, we had actually the eigenvalue problem. This is the eigenvalue of the Orselstein-Uhlenbeck operator, okay? And this is exactly 1/4, right? So if you take this integral, which is actually the generalization of the elliptic one, right, which is already in the appendix of paper, you can, okay, oh, there's a missing page here. No, okay. So this phi, this integral, you take the derivative with respect to time, right? And this is monotone. If you write it out, there, the eigenvalue problem comes handy, because that makes this derivative bigger or equal to 0. And then we do it as in the elliptic case, right? And we get that we get the uxn to be 1/2. Okay. Now, for the local case, for the local situation, this was the global. I took the obstacle there to be 0. All right? So for the local case, even in the elliptic case, you needed the C alpha alpha over 2. The C alpha regularity of your solution, right, in order to improve. Okay? So you need the gradient to be C alpha. Well, actually, the alpha is going to be less or equal to 1/2, but when you do the problem, you don't know that. Okay? Now, this was done a long time ago, and in a more general case where Arkhipova and Uraletsva take a general f on the right-hand side, they do the same thing, and they get the C alpha of the gradient. Now, so one thing you need for the proof is this, and the other thing you need this. You want to say, right, that, okay, in the elliptic case, we had that the origin was not in the convex hull of the uxn be less. You see, uxn has to be negative on the free boundary, right? And if you give it a little space here, the negative, then the origin in the elliptic said was not in the convex hull. Here, we need it for the whole line segment, because when you do, you take the derivative and things like that, you have to go a little bit in the past in order to use your eigenvalue problem, right? So here, in order to achieve this, you need that the ut plus continuity, the C alpha actually, okay, the C alpha you get for this, it's not the same alpha here, but since you don't know, you take the minimum alpha and it will do. Okay? So the C alpha continuity of this will give you this result. All right. All right, so the lemma says that these, okay, you have to localize the problem here. This is the parabolic, of course, yeah. And just like in the elliptic case, what you get here, don't get the monotonicity exactly, but you get that if phi t is less than that, or phi r is this, if this is that. So, and then you, in an argument, bootstrapping, going back and forth, then you can increase it to get exactly 1/2. Okay? Now, let me say, let me say that if you use the parabolic Armstrong's monotonicity formula, right, and you can, in the spirit as in the elliptic case that Caffarelli, Salsa, and Sylvester have done, you can achieve the same result as, as there, by working with the Almgren average monotonicity formula. Okay? So it's a paper that I think must have appeared or something. Okay. Now, our goal is the free boundary. I don't know if you realize from the beginning. And if you want to say something about the free boundary, a parabolic, I mean, any problem that has time depending, it's like you have a front, the front moves, right? So the speed, see, if everything would be smooth, the speed will be like minus ut over u nu, the direction there. So if you don't know anything about ut, I mean, there's no hope you can say anything about the free boundary, right? So we know that ut plus, right, is continuous, say alpha. ut minus, well, as the counterexample shows in the thick obstacle, cannot be continuous, right? You want to look at the you want to say something about the free boundary. From the very beginning, from the long time ago, the seminal work of Luis in Acta Mathematica, right? You need some kind of a condition, right, at the free boundary point in order to be able to say regularity. All right? So here we say, we take a point of parabolic density, positive parabolic density. So from the past, okay? And there we can prove that ut is continuous. Not only ut is continuous at a point, even from the future at a point. Okay, how do you do that? All right. You penalize again, differentiate with respect to t. Okay, so this is the equation inside, and this is on the boundary, on the Rn minus 1 where this obstacle holds. Okay, the v is the t derivative, of course. And you have to be careful how you take the cubes here, right? And you have to multiply with an appropriate test function. One is a cutoff function, a standard cutoff function. You have to be a little bit careful that in the t direction is increasing or something, you can take it like that. And then you take the fundamental solution, right, at any point, right? Okay, let me go back. Yeah, you see, you take this point, which will play the role of the pole, to be in 1/5 of this ball. Okay. Now, so, okay, this is a standard cutoff function. Now, this is the fundamental solution of the heat, but you cut it in what do you call that, heat balls. So this is the, wait a minute, yeah, the heat ball. Oh, I'm saying here, yeah. This is the heat ball. Heat ball, it's like this. Okay, so this is the tau, up, right? And this is the radius delta, I'm saying. The boundary of that, right, is the level surfaces, right, of the fundamental solution, right? So what do you do? Outside, right, is you take it to be exactly the fundamental solution. So when you enter here, you cut it with this function, right? Well, this is more or less, imagine this, maybe I'll write it here. Suppose here is the, let's say, the t will be in this direction. So let's take, so I don't know if I can do it, right? So the fundamental solution will be like that. So somewhere here I cut it, right? And then I take it, oh, it's better if we do it like this. Sorry. So, and then you go inside like this, and grows, and at the point goes to infinity, right? And then somewhere here, you put the heat ball, right? And you cut it here with this function, right? So your G delta is this, right? And this is smooth enough, let's say, just you need only the derivative, actually. It touches first order continuity with that. So this is this function, the polynomial, or well, it's not a polynomial, with a logarithm, this function, okay? Now, yeah, this is the heat ball, right? Okay, now you take this function, right, this test function. Actually, you need to do a little bit more approximation in the sense that with this cut off, right, of the fundamental solution, still the 0, 0 goes to infinity, right? So it's not smooth everywhere. So what you do, it's a technical, it's a nice exercise for a graduate student. You translate a little bit outside of your domain, so the pole is outside, right? And with some epsilon, another epsilon, and then you push it inside after you do the calculation or something. The same thing you do, of course, with this approximation. Okay. So, all right, let's see what happens now. All right, so when you multiply integrate by parts, right, this standard ritual we do in PDs, right, you get this. Actually, if you didn't have the delta, here would be the function itself at the pole, right? But you cannot do that because you want to let epsilon to go to 0, and we don't have point-wise convergence. Therefore, that's the idea of the delta. You get at the average over the heat ball, right? And then you let epsilon go to 0, and then delta go to 0. So finally, you get this. So On the left-hand side, you have the fundamental solution. Okay, well, yeah, the fundamental solution. Okay, you have to take the supremum over here, right, the points. And then, okay, maybe the 0, 0, it's not part of the supremum, but it's less. So if it holds for the supremum, it holds for the other one. So we have this estimate. So you have the gradient square integrated over the fundamental solution, and then you have the supremum in 1/5, and then you have that. Now, we want to control this integral by something of this sort. Now, how do we do that? We go back to the equation, we multiply with the appropriate test function, right? And we get an estimate of this sort. Now, you can drop this, so you have this less or equal to that, and you use the Poincaré inequality. Remember the Poincaré, it's enough if you have a 0 set, right, even in a hyperplane. The positive density of the 0 set guarantees that in the whole cube we have, right? So using the parabolic Poincaré inequality, I can have this less or equal to this, and this term came from the non-homogeneous term, the f, okay? So you have that. And you integrate it. If you integrate it, just a constant. The change will be the constant. Right? So, now, let's use the fact that when t is like that, the fundamental solution is bigger than a constant, depending on the dimension. So, you go back and you throw it in there. This is bigger. Okay, you adjust the constant here and you have it here. Now, you want to add this part with this constant on both sides. That's what we do. You add this, both sides, and you get this iteration where lambda is smaller than 1. Right? And then, from that, you get the C alpha regularity of your UT. Now, UT negative, but UT positive we knew it. So UT is continuous at such a point. Okay. Now, free boundary regularity. We take a ball in X and T now, right? Not just a regular ball, a hyperbolic ball, let's call it. Okay? And the problem takes this form locally, right? You subtract this. We subtract this in order, when to use the argument, we see which argument we use. At the point where you blow up, it has to be 0. So you subtract appropriately the obstacle, right? So this can go to 0 at 0, right? That's a good candidate for a non-degenerate free boundary point. You know, the positive parabolic density is a good candidate. Why? Because UT is continuous there. So what we can do is the following. You take the UT, you throw it on the other side, and you work with the elliptic equation, elliptic Almgren monotonicity formula. Well, the elliptic theory has developed. This is for the homogeneous case, a non-homogeneous and fractional case. has been worked here, right? So now we can define our non-degenerate point. We take this number, right? It's well defined. You take the L infinity of the balls, or the hyperbolic balls, right? And then the definition is the following. It's called a non-degenerate free boundary point if it is positive parabolic density with respect to the coincidence set, and L is between 0 and infinity.
Is the R squared, is the same homogeneity in x and t in that?
Yes. Yes, this is Rx, RT. We blow up hyperbolic. You see, when you want to do, it's like what we did with Reese and Salsa in the Stefan problem, right? You cannot distinguish the x and the t. The free boundary, right, behaves hyperbolically. Because if you blow up parabolically, the free boundary disappears. The only thing you can get traces only on the x level, not on t level. Right? You have destroyed it. You kept the equation, but you destroyed the free boundary. What is the free boundary? Right? So in order to be able to keep, in a sense, the free boundary, you have to do that, the scaling. Right? So the major result here, right? If you take this blow up, right, and you blow up around a non-degenerate point, you get this, right? This is a traveling wave. It's a so suppose this is the 0, 0 point. So this could be like this, or could be like this, right? Or could be like this, right? So from here you have, this is on the hyperplane Rn minus 1, right? So this, the xn is outside, right? So this is your u equal to 0. This is the time, right? This is the time, right? U equal to 0, u equal to 0. Okay? Okay. Now, proof. The proof goes as follows. You extract a subsequence, and you notice that this subsequence converges uniformly on compact subsets, right? And then you look at the equation, the ut term disappears. So you don't have any more parabolic equation. You have elliptic equation at each t level. Okay? It seems there's no connection between them, right? Okay. Now you take a harmonic, so it's a harmonic, as I said, outside the 0 set, right? The 0 set is a convex cone. Why? Because of our hypothesis on the parabolic positive density, right? And it's a cone actually. It's a cone. Let me show the next picture, which I have drawn many. Okay. Could be like this, right? So all these cases are accepted at this point, right? Think of this cone, right? This is in x1 t space. In the rest, in the rest of x prime, if you take x, okay, you take x1, x, you have the xn and we have the t. So we look at this coordinate. In here, right, imagine coming out, right, and you translate the whole thing. The whole picture is the same. So it's, right, so this cone, right, can be extended in the x double prime coordinates is independent of that. Okay? Now, what do we want to prove, actually? We want to prove that none of these situations hold. Okay? We want to prove it's a half space, like we said in the beginning. Okay, let's go back here and see. We said this is a convex. We saw that. Now, at t equals 0, we can apply our elliptic theory. Right? So the Almgren's monotonicity formula, the elliptic Almgren's monotonicity formula. Why? Because we threw everything to the obstacle and non-homogeneous goes to 0 at 0, and the ut continues there and goes to 0 too. Right? So everything is easy since we have all this theory, right? And then is the supporting planes, as I saw in the next previously. So depending on the A and B must be non-negative. The small a and b could be anything. Okay? Now, step 1. No horizontal parts can exist. That means A, capital B, must be strictly bigger than 0. Why? What we have? We have at each t level, we have a harmonic function, a polynomial, a harmonic polynomial. So at each t level. So when we approach from below, right, the t equals 0, you must get 3 halves. Violates the continuity. So no flat from below. The same argument from above. So this cannot hold, this cannot hold, this cannot hold, this cannot hold, this cannot hold. So let's see what happens with these 3. Okay? The second step. For if fixed time t, when you go to infinity, because of the quasi-convexity that I have in any x and t, a pure derivative, I have the, what do you call, the lower bound, right? The upper bound comes what we call non-degenerate free boundary problem, right? The 3 halves, the supremum, the 3 halves. And below, you can get in an angle like that, any x you go there, even below 3 halves. I forgot there must be a 2/3 in front of the 3 halves, to be precise, right? So at infinity, at each time level, u is exactly 2/3 x 3 halves. Okay? All right, now, this is a very, if you go to harmonic courses and you study unbounded domains, one of the standard theorems is fragment Lindelof theorem, which says what? If you have 0 in some cone, right, and behaves like 3 halves, or some power, and the infinity must be exactly like this. Right? So convex cone is non-horizontal half space. Right? Why? I haven't finished. Here the UT continuity comes. If you look at this, let me go. If you look at that cone, you look at that, you look at that. So the derivative here as you approach and the derivative here as you approach it, right, will have a jump, the t derivative. So in order to not to have a jump, right, this has to be 0. So the omega actually is the speed of your free boundary at that point, right? So you have a half space. So that proves differentiability of the free boundary at that point. To prove continuity, okay, to go in the past, it's much easier than one to do in the future, but it's a little bit involved, so I will reserve it for the next time. So I thank you for your attention.
Thanks, Ioannis, for the nice talk. Is there